Alright, so we're going to begin chemical equilibrium, and honestly we're going to be doing equilibrium for most of the rest of the year, so get ready, it's fun. So with chemical equilibrium, one thing that's really cool just to kind of start off to show one way that it's significant, equilibrium is really everywhere, but you don't always recognize it. Have you ever thought about how babies breathe when they're inside their mothers? The answer has to do with how our bodies bind oxygen to hemoglobin. So when you breathe in, your body takes in that oxygen and it binds with the hemoglobin in your blood. And then when your body needs the oxygen, it reverses the reaction and lets go of the oxygen. Well, in babies, they have a special hemoglobin, fetal hemoglobin. I don't even know what the difference is. But one difference is that it binds oxygen more strongly. So we have these things in equilibrium called equilibrium constants, and basically that tells how far a reaction will go. So when we bind hemoglobin, we get oxygen, and then it's gonna make the bound version hemoglobin and oxygen. But in a fetus, you have your fetal hemoglobin and oxygen, and it's going to bind. And essentially what we're saying is in babies, this forward reaction is stronger than in adults. This up here is the adult version. So what that means is the mom will breathe in oxygen. It'll bind and everything. But this reaction, this stuff, really is going to head this direction very, very strongly, so it'll actually take that oxygen and bind for the baby. And in this way, what this means is the mom and the baby don't share blood. They can exchange oxygen without exchanging blood because the oxygen will kind of migrate across the barrier to the baby and be used up in this way, and the baby can store it. So obviously, it's way more complicated than that, and I don't know all the details, but it's kind of interesting. Equilibrium is really going to affect a whole lot of things. So, what is equilibrium? Well, in a reaction, you have different reaction rates, right? And we talked about equilibrium briefly in kinetics, how when you reach equilibrium, the forward rate and the reverse rate are the same. So when you reach equilibrium, what it means is that the reaction is going in the forward direction at the same speed that it's going in the reverse reaction, in the reverse direction. So a reversible reaction can go both directions, and dynamic equilibrium is reached when the forward rate is equal to that reverse rate. It's called dynamic because both the forward and reverse reactions keep going. So once they reach equilibrium, the reactions have not stopped. Remember, they're just going at the same rate, so it appears like they have stopped. Does that make sense? Your concentrations aren't going to be changing at that point because it's going forward and backwards at the same rate. So it hasn't stopped, it's just happening at the same rate, so it looks like it's stopped. Just because the concentrations of products no longer change does not mean that the concentrations of reactants and products are equal to one another at equilibrium. I cannot talk today, I'm sorry. So when you finally reach equilibrium, it does not mean you're going to have equal amounts of reactant and product. That depends on how fast the forward and reverse reactions are proceeding at that point. So we will get into that as time goes on. The equilibrium constant tells us the relationship between the concentrations of reactants and products. So basically, it's going to tell us which reaction is favored. This right here is how you calculate the equilibrium constant, and it is big K, as opposed to little k of the rate constant. So what you have here is you have the reactant concentrations on the bottom and the product concentrations on top. So it's the product concentrations raised to their coefficients, those are the numbers in front, divided by the reactant concentration is raised to their coefficient. So essentially, if you end up with more product than reactant when you reach equilibrium, you're going to have a larger K value. If you end up with more reactant than product, in other words, the reaction doesn't go very far, then that means you're going to have a small K value. So we call that the equilibrium constant. It is the ratio of the concentrations of the products raised to their coefficients divided by the concentrations of the reactants raised to their coefficients. So in this case, if we're trying to find the rate constant, what we would do is we would say, okay, the products are NO2, so we take that concentration and raise it to the fourth power, and multiply by O2. There's a 1 in front of that, so it's just to the first power, and then divide that by the concentration of N2O5 squared. And that is going to be equal to the K value. Hopefully that makes sense. So these are practice problems in this case. The products, carbon monoxide just has a 1. H2 has a 2 in front of it, divided by CH3OH raised to the first. This one down here is CO2 cubed times H2O squared all over C3H8 times O2 to the fifth power. All right, so what does it mean? Well, if the K value is a whole lot greater than 1, that means that you have a lot of product when you reach equilibrium and not much reactant. So that means this reaction is going heavily in that direction. You're going to have a lot of HBr and not very much of these. If it's a lot less than 1, so this is the big number, this is a small number, that means not very much product is going to be formed. It's a small number, so you got big numbers down here, small numbers up here. So that means this direction is favored. You're going to have a whole lot more of this when all is said and done. If K is equal to 1, neither direction is favored, and the reaction is going to go about halfway. And that's about it. So I think that's probably a good place to stop for now. Hopefully all that makes sense.